Well, my name is Mustafa Ipenguruz, and this is Lab 3 in Physics 2211, Black Hole. So here's just a quick overview of what I'll be going over. I'll first do an introduction or an overview. I'll go over the code and glow script model for part 1 and then do the results. The glow script models for part 2, do that results. Go over some possible errors and answer the questions what if or what does it mean. So unlike other labs, this lab has two parts, part 1 and part 2. In part 1, we calculate the mass of a black hole, and in part 2, we determine the initial velocity of a spaceship to leave the system that we set in part 1. There's two fundamental physics principles used in this lab, Newton's second law and the gravitational force. Newton's second law states that the acceleration of an object is directly proportional to the force upon it and inversely proportional to its mass. You can see that in the bottom left equation where it says F equals ma. The gravitational force is an attractive force between the two bodies and of mass at any distance, represented by the top right equation of gravitational force F equals g m1 m2 over r squared. A quick preview of my main results was that in part 1, I found the average mass of the black hole to be 8.30667 times 10 to the 33 power, and I found the ship speed x and y to be 0.2 times 10 to the 6 negative, and 8.3 times 10 to the 6 in the y direction to escape the system described in part 1. Some models I used in this lab was that I used experiments to try to find the numbers after doing the calculations for FNet and such in GlowScript. I used initial conditions for the gravitational constant. Mass of the star was 2 times 10 to the 30 kilograms, and the change in T was 86,400 seconds, which is just 24 times 60 times 60. In part 1, our system was the star, and our surroundings were the gravitational force from the black hole, and in part 2 our system was the spaceship and our surroundings with the gravitational force from the black hole as well as the gravitational force from the star. So here's just a glow script model for part 1 that we used. I set up the initial components and set the seeds for randomization. That's my email right there that I used for the seed. Star mass was given to us in the questions, and the time between the data points is just 24 times 60 times 6g, which is the amount of seconds in an Earth day. And here's GlowScript Model 1 continued. I changed the vInitial, vFinal, pInitial, and pFinal. I used those along with delta t to calculate FNet perpendicular and parallel. Then I used the mass of the black hole using the gravitation force to solve for mass. I also changed the arrows according to the position of the star. You can see that on the bottom left. So our results for part 1 indicated that the average mass for black hole was 8.30667 times 10 to the 33. This was an average of all the different forces we got. Our FNet was 8.2258 times 10 to the 28. Our perpendicular and parallel components are also below that. Here's the glow script model for part 2. Our inertial constants and black hole mass are calculated from part 1, so we just put that into vh.m as 8.3 e to the 33. And the ship speeds in the x and y direction are actually what we need to find, and I found those by just testing out with the completed set of code. Here's the glow script model in part 2 continued. We changed the r and the f the same way by using gravitational force times magnitude of distance traveled, and the net force was found by combining the forces of the things that act on the system. For example, for FNet on planet, we did FBH on planet plus FShip on planet, which was the FNet for that thing. Our results for part 2, as you can see on the right side, when x is negative 3.9 times 10 to the 7 and our y is 1.52 times 10 to the 6th, for our velocity, the purple line represents the spaceship, and you can see it just barely misses the black hole and escapes the system. Some possible errors are that accuracy of a simulation in comparison to real life. I mean, in real life, there's lots of more factors affecting the, a system than just something like simple as a black hole and a star. So that was obviously not represented here. That can be a possible error. And the amount of time spent on trying to find the velocities and trying to get as close to the black hole could also be more. So that would allow us to get more precise and accurate measurements on what the velocity needs to be in the x and y directions to get closer to the black hole. So what if or what does it mean? What initial velocity is needed for the spaceship to orbit the black hole? I again found this by trial and error, and on the right side you can see the purple path, the orbit that the spaceship took. The ship speed I set to negative 0.2 e to the sixth, and in the y direction I set it to 8.3 times 10 to the sixth, and that allowed it to do a full orbit continuously around the black hole. How is the net force and its parallel or perpendicular components different from the rate of change of momentum in its components? So for the rate of change of momentum, systems change in velocity. But for the net force, we don't know which outside forces are making an impact on the system, so we need to consider that. And thank you for watching.